Hello, class. Today we're going to be discussing applications of derivative. This is where derivatives come into real-life situations. And today I'm going to be doing two examples for you from your textbook on this concept, applications of derivative. Now, before we get started with the problems, your textbook outlines a process for dealing with minimum and maximization problems. So this is a proposed method in your text for dealing with these problems. It's not a one-size-fits-all method, but it's definitely where you want to go if you get stuck or aren't sure how to start. So the proposed method one has you to understand the problem. So read and think about what's happening in the problem. Secondly, we're going to develop a model. So this is a mathematical model of the situation. So the first step in my mind is draw a picture. This particular point I cannot underline enough. In fact, I'm going to highlight it. Draw a picture whenever a picture makes sense, which I think is in more cases than you allow. Now, you're going to assign the unknowns in that picture with as few variables as possible. What this means is that you are going to want to introduce a variable, and then if you can, represent other quantities in the situation based on that particular variable instead of introducing a new variable. For example, old school problems would say you have two consecutive integers. Instead of saying the two consecutive integers are x and y, you would call one x and the other x plus 1. Therefore, you're using as few variables as possible because you can relate the other unknown to the original without introducing a second variable. You want to write a function that represents what is going to be maximized or minimized in the problem. Again, in business and in economics, they want to minimize or maximize the results while minimizing the cost. For example, I want to maximize the size of this carton of milk while minimizing the materials so I can make the biggest milk carton to fit my needs for the smallest amount of money. So that function is going to represent whatever quantity you want to minimize or maximize. I suggest you graph the function before you do anything else. You can get a look at what's happening. You're going to find the critical and endpoints of this function. I would prefer you to do this analytically whenever possible so we can practice our derivatives and practice finding the critical points by hand instead of just doing trace on a graph. You're going to use the critical and endpoints to solve the problem. And I bolded answer the question because a lot of times you're so into the problem, you forget about what the question is asking you. So in the end, you want to revisit the question and answer it, giving not too much nor too little information to answer that question. All right, so we're going to take a look at one question from your textbook first. What is the largest possible area of a triangle whose hypotenuse is 5 centimeters long, and what are its dimensions? So how can I maximize the area if my limitation is that the hypotenuse is 5 centimeters long? Okay. What do you think is below this? Yep. Very good. Understand the problem. Draw a picture. So here I have drawn a picture of a triangle. It is a right triangle because it mentioned the word hypotenuse. So we know the hypotenuse is 5 centimeters long. So I'm going to label the hypotenuse as 5 centimeters. Now, I'm going to have to introduce and assign an unknown. So here, if I'm taking a look, I'm going to assign an unknown. Clearly, one of the sides is going to have to be an unknown. If I knew all the sides, there wouldn't really be a problem. So I'm going to assign this side to be x centimeters, and you can pick whichever one. Now, as you know, in order to find the area of a triangle, you need the height and the base. Or in terms of a right triangle, you need the two legs. It's 1/2, one leg times the other leg. Since those are perpendicular, those would be the height and the base. How can we represent this side without introducing a second variable? Well, you can consider the fact that this is another leg in my right triangle. So if I were to say, hey, I know that leg squared plus x squared equals 25. So in other words, Pythagorean theorem says one leg squared plus the other leg squared equals 25. So I can write that my leg equals the square root of 25 minus x squared. Okay, so I don't have to introduce another variable for that leg. I can simply solve for that leg given that I assigned this side to be x units long and this side to be x centimeters long and this side to be 5 centimeters long. Okie dokie. So now I have a picture. I'm going to go ahead and move this. Oh, let's see if I can do that. Here that is. And I'm just going to get rid of that. Sorry. There, let's do this. So we have that this leg is the square root of 25 minus x squared. This leg is x, and this is 5 centimeters long. Now, when I consider the area, because if you look at your steps, we drew a picture, we assigned the unknowns with as few variables as possible. Now I would like to write a function that represents the quantity to be minimized or maximized. Well, what we would like to minimize or maximize is the area. So let's write a function that represents the area. Okay, so I'm going to write that the area in terms of my side x is 1/2 the base times the height. So it's 1/2, I'm just going to write the x first, times 25 minus x squared. All right, so we're going to find the critical points of this function. Now, what I would suggest you do at your desks is actually go ahead and graph that function in your graphing calculator. I'm going to consider finding these critical points without using the min and max functions in the calculator. I'm going to actually do them by using calculus. So when you consider this function, you should consider if there are any limitations on x. Well, x actually has to be between -5 and 5. Whoa, sorry, forgot the x there. -5 and 5. Those are my endpoints. The reason being is that you cannot take the square root of a negative number, at least if you want the answer to be real. So I know in reality this for that function is or equal to. However, in this case, if this leg equaled 5, we would no longer have a triangle. It would be, this side would be nothing. So I'm saying that x has to be from -5 to 5 just to recognize the real life situation here, where if you have a triangle, sorry, that's still a minus, if you have a triangle and the hypotenuse is 5, the legs both have to be less than 5 centimeters long. Okay, so these are my endpoints. Let me just go ahead and draw a quick graph. Ooh, messy, sorry. The function looks something like this. So that is my function. Notice it does go through the origin, 0, 0, because if my input is 0, my output will be 0 as well. Hopefully you have a better drawing on your own paper. This is again, tough to do with the computer tablet. So we can say that if this is the area, it's going to be maximized here because it's the high point. So I'm trying to find the place where I will have maximized, maximize this area. So I'm going to find this particular point. All right, so let's use calculus to find that particular point. Is there a better way that I could write this area function and have it be easier to differentiate? I say this because currently I need the product rule, because this is the product of two different functions. It's the product of 1/2 x and the square root of 25 minus x squared. I'm thinking if I bring the 1/2 x into, or actually the x would be good too. If I bring the x into my square root, I don't have to use the product rule. So let's take a look. If I bring the x into the square root, what would it become? Well, the square root of what is x? The square root of x squared. So I bring the x into the square root, it's x squared, and that's 25 minus x squared. So there is that function. So now I'm just going to clean it up a little bit by distributing. That's 1/2 times the square root of 25 x squared minus x to the 4th. And do note, if I pull that x squared out of the square root, I would have what I started with over here. All right, so now I'm going to rewrite yet again. It's 1/2 times 25 minus, x squared minus x to the 4th. And all that is to the half power. Because we know that when we differentiate, it's easier to have it written as a power than as a radical, because then we can apply the power rule. So now we are ready to take the derivative. I'm going to differentiate. I'm going to multiply the power times the coefficient. I get 1/4 times 25x squared minus x to the 4th to the negative 1/2 power. Am I done? Nope. You need to differentiate, the inside. So differentiating the inside is doing the chain rule. So this is 50x minus 4x cubed. Okay, so a little messy. I apologize for that. The derivative is 1/4 of 25x squared minus x to the 4th. Bump the power down by 1 to the negative 1/2 power times the derivative of the inside function, which is 50x minus 4x cubed. All right, so now I'm going to clean this up, and I'm going to write that my derivative function is, well, my numerator is 50x minus 4x cubed. My denominator is 4, because of the 1/4, the 4 in the denominator of the original fraction, times the square root, because that's the half power, the square root of 25x squared minus x to the 4th. All right, so again, this did not have a negative power, so it went in the numerator. Oops. Okay, take a look. Let's do orange now. This had a negative power right up here. So that goes in the denominator with a square root. And then, let's do green. The 4 is in the denominator here, so the 4 is in the denominator there. So that's how I got that expression for the derivative of the area. Now, I need another page here. By looking at the graph, we know the endpoints the 5, oh, and actually this graph could be a little more accurate. At x equals 5, this is 0. So even though my graphing calculator doesn't take me all the way up here, we know that if x is 5 or x is negative 5, I'll do 25 minus 5 squared or 25 minus negative 5 quantity squared. And either way, I'm going to get 0. So we notice here that our two endpoints are not going to be mins or maxes. Okay, so those are not important. Our critical points are going to be important because we can see this second critical point where the derivative equals 0 is a maximum. So let's find it. Let's find where the derivative equals 0. So I can write that a prime of x equals 0, and that would equal 50x minus 4x cubed. Okay, so let's factor out, let's say, a 2x, and what we are left with is 25 minus 2x squared. Okay, so I'm actually going to have 3 critical points at 2x equals 0 and 25 minus 2x squared equals 0. So I have a critical point at x equals 0, and I'm going to solve this one. I get 25 equals 2x squared, and 25 halves equals x squared. Take the square root, and I get plus or minus 5 over the square root of 2 equals x. And so these here and here are all critical points. Okay, now I'd like us to consider the graph again. So if I go back to my graph, let's just go one back, I have a critical point here. Perhaps that's a change in concavity. Sure looks like it. I have a critical point here, which is a absolute min, and a critical point here, which is an absolute max. So when I'm considering my steps that I outlined in the beginning, it said to graph it, which we did, identify the critical and endpoints, which we did, and then basically solve it and interpret the solution. Okay, so it wanted to know when the area could be maximized. Okay, so we know at x equals positive 5 over square root of 2, we have an absolute max. So consider on my graph, I have an absolute max. It was like about right here. Okay, and what they wanted to know is the dimensions of my triangle. Well, here's a little sketch of the triangle. Okay, x was right here, and that's 5 over square root 2. The other dimension was the square root of 25 minus x squared. Well, x squared is 25 halves. Wow. The square root of 25 minus 25 halves is the square root of 25 over the square root of 2. So that, ladies and gentlemen, is going to be the same thing. The square root of 5, I'm sorry, not that. It's going to be 5 over the square root of 2. Okay? So the triangle's area is maximized when the two legs are the same. So, sorry, I keep doing that. So now we know that the dimensions are 5 over square root 2, 5 over square root 2, And so that's kind of my triangle dimensions. And then my area is simply, I can plug it into my area function, or I can do 1/2 times each leg. So my area is 25/4 centimeters squared. So I should probably label these centimeters and centimeters. Whoops. Okay, so here are my dimensions. Dimensions and area. Okay, so did I answer my question? It asked what the dimensions of my triangle were and what my maximized area would be. Okay, so that is one problem start to finish. All right, so now we're going to do one more problem from your textbook. This is number 6 on page 214. So we have a rectangle with a base on the x-axis. So I think you're anticipating what might be behind curtain number 3. Here we go. And the base of the rectangle is on the x-axis, and its two upper vertices are on the parabola 12 minus x squared. So I used the graphing calculator to get a nice sketch of this. I couldn't draw one by hand that was nice. And if you consider a rectangle inscribed in that, it would basically look something like this. Okay, where you have a rectangle whose tops two vertices are on the parabola. Oops, oh, I almost had it. We had a rectangle whose upper two vertices are on the parabola, and then the lower two vertices are on the x-axis. Okay, so there we go. That's close enough. So what is the largest area the rectangle can have, and what are its dimensions? So again, first step is understand the problem. How can I maximize this rectangle that is trapped under this parabola, where the vertices are here and here, but they can go anywhere. They can slide anywhere along that parabola. So I could just slide and make a different rectangle, okay? And my two vertices down here are stuck on the x-axis. How can I have the biggest rectangle as possible in terms of area? Well, let's follow the steps. The first is to understand the problem. The second step is to draw a picture when we're creating our model. The third step is to assign variables. So I am going to be smart and call the x-axis variable x, okay? And that will be the distance from 0 to one vertex of my rectangle. Now, if from here to here is x, we have to consider that the base of this rectangle is not x, it's actually 2x. Because an entire base of a rectangle is the distance from the y-axis to this vertex. So you have to go the other way as well. And because of the symmetry of the parabola, the x in one direction, the distance in one direction is the same as the distance in the other direction. Now, if we are to consider the height of this parabola, well, what is the parabola height related to? It's the same as the height of the rectangle. So if I know the function is given by 12 minus x squared, that's the y value at any point on my parabola, then the y value, or the height of the rectangle, is given by 12 minus x squared. Because again, this vertex and that vertex are tied directly to the height of the parabola, which is the y value of the parabola, which is 12 minus x squared. Cool, huh? So what are we maximizing? Area. And I'm now writing an area expression in terms of x, because I have both my length and my width in terms of x. So area is simply length, or that's the width, times the length. And when we consider that particular function, we know it will be easier to differentiate. I won't have to use the product rule if I distribute. So this is 24x minus 2x cubed. And now I can consider this area function, and I can consider its critical points and its endpoints. Now, x is limited. X cannot be wider than the parabola is. So this 0 is at the square root of 12. Because if I plug 12 in here, the square root of 12 squared is 12. 12 minus 12 would give me a 0. And this 0 is the negative square root of 12. So I know I'm really just considering x values from the negative radical 12 to the positive radical 12. So that's going to be important, because if I get a critical point outside of this, who cares? It doesn't matter. All right. I would go ahead and sketch the graph of this function. So I'll leave you guys to do that. But I would like to take the derivative and consider my critical points. I know these are essentially the endpoints of my model. So my derivative is 24 minus 6x squared. So I can set my derivative equal to 0 to find my critical points, and I will have 2 of them. So solving, I would get, and let me come up here, I still have some room on this page, I would get 6x squared equals 24, and x is going to equal plus or minus 2. All right. So what that means is I will have a critical point at x equals plus or minus 2. And I'm not going to consider negative 2 because at negative 2, I'm really just considering the distance along my x. So at negative 2, that would make this length a negative length, which doesn't make any sense at all. Okay, so if we consider this a length, the distance from this vertex to this vertex is going to be 4. So let's just consider x at positive 2. And then if we look at our rectangle, which I'll redraw for clarity's sake, holy guacamole. Okay, let's grab a real rectangle. There we go. And I'm going to page over a little bit. So if we consider the real rectangle, we know that this side is 2x. So if x is 2, this side is 4. This side is 12 minus x squared. So this side is 8. So an 8 by 4 rectangle maximizes the area. And the area then is 32 square units. And you will note, if you graph the function at x equals 2, you'll have a maximum. And it actually will just be a local max because the function is cubic. So you're not going to have any absolutes there. So to answer the question, it said, what are the dimensions of the rectangle and what is that maximal area? Well, the maximal area is just length times width, 32 units squared, and then the dimensions are an 8 by 4 rectangle. All right, so your homework assignment is behind curtain number 4. Ta-da! All right, so these problems are quite involved, especially as we get to the ones that are a little more intense. So these actually make up quite a few problems. So what I would like you to do, let's go big with this so you can really see it. So it's page 214 to 215, 1 through 17 odd, 21 is a bonus. Now, what I'd like you to do is work for the rest of the class period on the assignment. When you go home, I want you to work about 45 minutes on calc, on these problems. Tomorrow, you'll be able to work together to finish it. So it's going to take you much longer than the rest of class in 45 minutes to finish all these, but that's why I'm giving you tomorrow during the day to work out some of the more difficult problems in particular. Okay, so I will see you tomorrow. Good luck with this.